Circuit theory might seem like a standalone subject, but it actually originates from electromagnetic theory. Every equation we use in circuits, starting with Ohm's law, can be traced back to Maxwell's equations. Understanding this connection gives you a deeper appreciation of why these formulas work. In this first video, we'll derive Ohm's law, V equals IR, directly from Maxwell's equations. Then we'll define current and the capacitor voltage-current relationship. Finally, we'll introduce the 4 types of circuit sources you'll encounter throughout this course. Let's begin with one of Maxwell's equations, the curl of H. In full form, it reads curl H equals the time derivative of D plus sigma times E plus the external source current density, JES. Sigma E represents the conduction current density. Sigma is the material's electrical conductivity measured in Siemens per meter. E is the electric field in volts per meter. JES is the current density from external sources in amperes per meter squared. In a DC circuit, nothing changes with time, so the dD/dt term drops out. What remains is sigma E equals JES. Now let's examine the units on each side. On the left, Siemens per meter times volts per meter gives us Siemens times volts over meters squared. On the right, amperes over meters squared. The meters squared cancel from both sides. Now, conductivity sigma is the inverse of resistance. Sigma equals 1 over R. And the current through a cross-sectional area is just I. Substituting, 1 over R times V equals I. Multiplying both sides by R gives us V equals I times R. And there it is, Ohm's law, derived directly from Maxwell's equations. Now let's precisely define what current means. Current, I, equals dq over dt. It is the time rate of change of electric charge. Physically, it tells us how much charge flows through a cross-section of a conductor per unit time. If 1 coulomb of charge passes through in 1 second, that's 1 ampere of current. This dq over dt relationship is fundamental. Every time you see a current in a circuit, remember, it represents charge in motion. A capacitor stores energy in an electric field between its plates. The charge stored relates to the voltage across it by Q equals Vc, where C is the capacitance in farads. Now, what happens when the voltage changes with time? Let's differentiate both sides with respect to t. On the left side, dq over dt is simply the current flowing into the capacitor, which we call IC. On the right side, C is a constant, so it stays outside the derivative. We get C times dVc over dt. Therefore, IC equals C times dVc over dt. This is the capacitor's constitutive equation. Notice something important. Unlike a resistor, where current depends directly on voltage, a capacitor's current depends on the rate of change of voltage. If the voltage is constant, no current flows through the capacitor, no matter how large that voltage is. Every circuit needs sources to drive current and establish voltages. There are 2 categories, independent and dependent. An independent source provides a fixed value regardless of what happens elsewhere in the circuit. We represent it with a circle. A dependent source, also called a controlled source, produces a value that depends on some other voltage or current in the circuit. We draw it as a diamond or rhombus shape. For voltage sources, plus and minus signs indicate the polarity. For current sources, an arrow inside shows the direction of conventional current flow. This gives us 4 types in total: independent voltage source, dependent voltage source, independent current source, and dependent current source. You'll see independent sources in most basic circuits. Dependent sources become important when modeling transistors and operational amplifiers. Let's wrap up with the key takeaways. Ohm's law, V equals IR, comes directly from Maxwell's equations. It's not just an empirical rule, it has a theoretical foundation. Current is defined as the rate of charge flow. I equals dq over dt. The capacitor current voltage relationship is IC equals C times dVc over dt. And we have four source types, independent and dependent, each in voltage and current variance, drawn as circles and diamonds, respectively. With these building blocks in place, we're ready to start analyzing circuits in the next video.